It's working. So, hi everyone, this is Vishal, and I will start a new chapter, a new topic that is group theory. So, before going into group theory, let us discuss the binary composition. Uh, we usually denote it by this symbol, and this is nothing but a function from a set that is G cross G to G. G is not equals to 5. Is a non-empty set. Okay. So binary composition is a function from G cross G to G. So for any pair A comma B in G cross G, and we are operating the function on A comma B, that is usually this thing we usually denote it by A composition B. That is, we are taking the composition of A and B, and since this binary composition, as I said, is a function, so obviously the resultant is always in G. Okay, and this thing that for all A comma B in G and a composition B is in G, so uh, this thing is called closure property. It is called closure property. What does that mean, closure? Closure means nothing that you are taking two elements and taking the composition. It is, and you find out that the resultant is always in that set. That's why it is called closure. That it is closed under this composition. So, since usually in books or something, when you are reading the definition of group theory, not group theory, definition of a group, the first condition that a group set, non-empty set, must satisfy to form a group is that the closure property. Okay, the closure property is the first thing or the first condition that must be satisfied by the set and the composition. And since I already uh, told you that it is a function which is maps from G cross G to G, so it is very clear that if I say if I write this as order pair G and composition, and it is binary composition, if this symbol denotes a binary composition, then it is obvious that it satisfies closure property. Okay, now let's move on to the second topic. Sorry, not second topic, second property, that is associativity. Associativity. And what does that mean? And here you have to take three or maybe four, doesn't matter how many elements. I am randomly choosing three elements from an oriented set G, and we are taking composition of A and B first. Then with the resultant, we are again taking composition with C. Okay, this must be equal to A composition, B composition, C. That is, here first we are taking the composition of A and B, and with the resultant of that, we are again taking composition of C. Okay, and here we are taking the composition of B and C first, and then taking composition of with A. So if this condition is true, that is these two values are same, then we say that G together with the composition satisfy associativity. Okay, satisfies associativity. This is the second condition. This is the second condition that must be satisfied by the binary composition and the non-binary composition. Second condition. Now let's go to the third. That is identity property. Okay. So the non-empty set G must contain an element. You usually denote the identity element by E, so I am using this symbol. So this E must be in G, but that means that G should contain an element E such that whenever we are taking the composition of any element or for all element A in G, when we are taking from left the composition and from right, the resultant is should be always equals to A. Okay. Here this E is fixed. Okay. This E is fixed and you are changing A. Okay. You are changing A and for each A we are getting the same result. If we get the same result, then we say that this E is called is identity element. Okay. And this group G contains the identity element, so it satisfies identity property. And this is the third condition. And let's move on to the last condition, that is inverse. Okay, now what is inverse? For all element A in G, there must exist element B in G such that A composition B is equal to B composition A equals to E. Where E is the identity. That is, uh, if we take any A from G, we will get a B according to that, such that A composition B and B composition A is equals to E. Okay, then we say that this B is the inverse of A, and usually we denote it like A inverse. Okay, or A to the power -1. Okay, and don't think it as 1 by A. Okay, this is just a symbol to denote that this means inverse of A. Okay, so we have discussed the four properties, that is closure, identity, associativity, and inverse. If these four properties satisfies by any pair of non-empty set together and a binary composition, then we call that pair G with binary composition is a forms a group. We say this forms a group. Okay, and for example, let's take the set of all integers. Okay, okay, not set of integers. Let's first start with the set of all positive integers. That is natural number. This n. Okay, what is n? Is 1, 2, 3, 4, 5. Now, if we take composition as addition, usual addition that we are doing from class 1, and if we take any two elements from natural number, the result, and if we add them, the result is always always a natural number. So closure property is satisfied, and the associativity part, it is also we have used this property without knowing the name of the property from childhood. So I'm not going to prove. And notice here you can see it doesn't contain any identity element. Okay, it doesn't contain any identity element. So this the set of all natural number with respect to addition doesn't forms a group. Now if we change this addition to multiplication, then also you can notice that the closure and the associativity, these two things are already satisfied. And also this natural number, in the set of natural number we can get the number 1, that is the very first element of natural number. And take any natural number n, and n multiplied by 1 or 1 multiplied by n is equals to n. That means this 1 works as a identity element. Okay, this one works as a identity element. So this set of natural number with respect to addition only satisfies two things, closure and associativity, and doesn't contain the identity, so it is not a group. But when we change the binary composition from addition to multiplication, we get that we have noticed that it does contain the identity element. Now only one more condition is left, that is inverse property. If the set of natural number satisfies inverse property, then it will form a group. But unfortunately or fortunately, that doesn't matter. But in set of natural number, you can't find the multiplicative inverse of any element. Because we know, if we take, let's say, 2, then if we multiply 1 by 2, 2 with half, we will get the result 1. But this half doesn't belongs to set of natural number. So the set of natural number doesn't contain or doesn't hold the inverse property. Though the one inverse exists, because one inverse is basically 1, and uh, it is a theorem, you can say, that is let's say, and one is the identity element, na? So for any group G with respect to binary composition, E composition E equal to E composition E. Basically, I am changing from left to right, right to left, but since these two elements are E, you can't say which element, which one is on the left and which one on the left, right? But you can see this is equal to E. Okay, so, and what can we say from this equation? That is, the E is self-inverse. E is self-inverse. Okay, so basically E inverse is also E. This is a theorem, you can say. And also, always remember this E, the identity element of G, is unique. Okay, it is unique. That is, a group will contain only a single identity element. Okay, now we are at inverse property of natural number, and we have seen that the set of natural number doesn't contain the doesn't hold the inverse property. So to show the set of all natural number with respect to multiplication, again doesn't form a group. Now let's move on to a much little bigger set, that is the set of all integers, usually denoted by Z. And again I am taking, okay, first here first we have we take the binary computation as multiplication. Okay, and if we take any two elements from integers and take their multiplication, the result is also in the also an integer. So associativity and closure property always holds in set of integers, and we have we used this property several times in our childhood. So let's see if it contains identity or an inverse of each element or not. Yeah, so since we have seen that one belongs to natural numbers, so one belongs to Z, and for Z also, if we take any integer and multiply with 1 from left or right, the resultant is always equals to n. We know that. So the identity element is 1 and it exists in set of all integers. Now again, you can notice that for any integer, we will not get the inverse except 1, and we know, oh, there is a thing. Yeah, okay. So with this multiplication, it doesn't form a group because it doesn't contains inverse element of each element. Even it doesn't contain the inverse element of 0 also. 0 belongs to Z, no? And it doesn't contain the inverse elements of 0 or any integer that is not 1. So it doesn't form a group. Now let's change the binary composition to addition. Here the first two properties are satisfied, and in case of addition we will get identity element as 0, because we know if we add 0 any number, we will again get that. We will get that number. So 0 is the identity element here, and surprisingly, this forms a group because, not surprisingly, but this forms a group because for each element n in integers, we will get minus n, and if we add these two, we will get 0. Even if we add minus n plus n, this thing is also 0. So for each element in Z, we are getting the additive inverse. Okay, so Z with respect to addition forms a group. Now let I will show you a thing that is NA. Okay, where n belongs to integers and G is a group and A belongs to G. What does this mean, NA? This means nothing but this means nothing but composition of A n times. Okay, this means composition of A n times. Now, uh, 2-3 definitions. That is order of a group. Since G is a group, so order of a group. What is order of a group? It is nothing but the number of elements of G. And order of an element where A belongs to G is nothing but the smallest some smallest integer, the smallest positive integer, sorry, belongs to Z plus smallest positive integer, such that NA equals to identity. Okay. It's called the order of the element A. Okay, and is this theorem that says that order of each element of G must divide order of G. Okay, so if A belongs to G and order of A exists, then order of A must divide order of G. And why I'm saying exists, because I say just a few seconds ago, a few minutes ago, we have seen the set of integers with respect to addition. It forms a group, and if we take, let's say, 1 belongs to Z, and if we take n1, that is 1 plus 1 plus 1 plus 1 n times, it will be equals to n, and this can never be 0 unless and until yeah, this thing can never be 0 where n is a natural number. So so order of A doesn't exist here. So for any group, the order of element is not guaranteed. We will not always get the order of an element. That's why I say if order of A exists, then this must divide the order of G. Also, if in just for example, what is if we are taking G as a set of integers, what is order of G? It is equals to A, or the cardinality of natural number. We know, right? The cardinality of natural number and cardinality of integers are same. That is, both of them are countably infinite. And so since this side we have infinity, so if we take any element, any natural number, well, this will automatically divide, you can say. Okay, so if exists, then good. Not exist, doesn't matter. Now let me show you another property of group, or another condition that we can attach with the definition of group, that is A composition B equals to B composition A. If this condition holds, then we say that G is abelian or commutative group. And we have already seen that Z plus is a group. Here if we take 1, and I have already told you what is NA, so I am taking A as 1, then we will get 1. We will get N. So basically what I am saying, that I can generate the each and every element of Z, by using 1. And how? Just do NA where N belongs to Z, right? So this element 1 generates the whole Z, generates the whole Z. So since it's generating the whole Z, so I can say 1 is the generator. What is 1? 1 is the generator. Okay, so from this there is another definition, that for any arbitrary group G with respect to condition, if we get an element A in G such that in A such that for all B belongs to G, there exists a integer or natural number, whatever you say, is a natural number, such that NA equals to B. If this condition holds, here A is fixed, and arbitrarily we are choosing B from G, and what we can see, that I using A just by taking binary composition n times of A, we will get B. So basically using A, I can generate the whole set G. If this condition holds for any group, then G is called cyclic. And remember, if G is cyclic, then G is abelian. So if G is cyclic, then G is abelian. Okay. And the element, let's say G, and G belongs to G such that Ng is equal to B for any B, there exists N belongs to figures. Here this G, by using G we can generate the whole group capital G, so this G is called the generator of the group G. And there is an interesting fact or a theorem, that is order of G in G is exactly equal to order of the group. Okay, so if you are asked, if you are given any group, and if you are asked that tell me whether this group is cyclic or not, just try to find the order of each and every element, and if you get a single element whose order is exactly equals to order of G, here the order of G must be finite, obviously. If this is infinite, then you can't say always can't say that is true, but this is finite, then you can check. If the order of the group is infinite, then there are infinitely many elements, and checking or taking each and every element of G and try to find out the order of that element is not a very easy thing, and not easy, it is impossible in your lifetime also. So this let me just tell you that this being the order of group, it must be finite, then you will at least may take 100 years, but you can at least compute this thing. So what you will do, you will take each and every element of G and try to find out the order. If for any element you get this result is true, then you can say that G is a generator. Okay, so that's it for today. I have today I have taught you the basic definitions of group theory, abelian group and commutative group. From next class, I will dive into more interesting and deep topics of group theory. Okay, so for today, it's done and bye.